Here we are going to look at one special coupling or a joint that is used for connecting two shafts meeting in a point at some angle, so that motion of one shaft is transferred to the other. Let us see its construction. Here the input and output shafts are shown in blue and green, and each one has a fork like this at its end, and sitting between these two forks, engaging with them through revolute pairs, is this red crosslink. The motion is then transferred from the input shaft to the input fork to the crosslink to the output fork and finally to the output shaft. Let us take a closer look at this motion transfer. For that, we are going to name the endpoints of the crosslink as A and B engaging with the input fork, and C and D engaging with the output fork. If we look along the input shaft, then the path of A and B will appear to be a perfect circle shown in blue, and the path of C and D will also be a circle, but it will appear as an ellipse because we are looking at it at an angle. Let us understand it step by step. First, we are viewing along the input shaft, so it appears as a point, and its fork ends A and B will be tracing a perfect circle. Let us take one of their arbitrary positions like this. So that is the position of the crosslink's arm AB also, and the crosslink's arm CD will be in a perpendicular plane seen here as a line. The position of C and D will also be somewhere on this ellipse traced by the output fork, and therefore at the intersection of this ellipse and the plane we will locate their position C dash and D dash. To find the angles turned by the two shafts, let us take an arbitrary initial position of the input shaft and measure the angle it has turned through, say theta. Then the angle turned by the output shaft appears to be phi dash, because we are not looking at its true path but a projected path. To get the true angle, we must project its apparent positions C dash and D dash on its true path, a circle, and then we will get these points C and D, and connecting them will give us the true angle phi. One can see that the angle turned by the input and output shaft are not equal. So in general, this joint will have a velocity ratio which is varying. The input shaft will turn uniformly, but the output shaft will not. Interestingly, when the input shaft has turned through 90 degrees, the output shaft will also turn through 90 degrees, assuming this position. That means in quarter of a cycle, the two shafts are in sync. So in half of that quarter, or 1/8 of the revolution, the output shaft lags behind, and in the remaining 1/8 of revolution, it catches up. And this happens 4 times in a cycle. Let us see this happen in an actual mechanism. So here we are looking at the 3D model from the top view, and let us give it quarter of a revolution. And now you can see this shaft has turned through 90, and so has the other. One more quarter revolution, and again this has turned through 90, and so has the output shaft. Variation of velocity ratio is a serious drawback of this joint, called as Hooke's joint or the universal coupling. But it is easy to overcome. If a smooth input is giving us a fluctuating output, then a fluctuating input should give us a smooth output. This is done by connecting two universal joints in series. It is called as double Hooke's joint, and it is used for transmission of power in vehicles. The condition is the first and the last shaft should be parallel to each other so that the angle for each universal joint is the same.